Welcome, everyone. zetamath here, bringing you another puzzle of the week from a past stream. This puzzle is Sirius by Jovial, which I think makes the best use of the Sudoku X constraint that I've ever seen. I won't give away the technique that's used in the puzzle, but it's really neat, and I really encourage you to try this one if you're at all inclined to do so. As usual, I want to say a big thank you to all of our supporters over on Patreon. The Patreon really helps keep the lights on around here. If you'd like to become a patron, you can go to patreon.com/zetamath. Alternatively, we'll be debuting YouTube memberships really soon, so watch the channel for more information about that. I also really want to thank all of our subscribers who've just helped us get over the 1,000 subscriber milestone. I really love the community that we've built here, and I really encourage you, if you've not yet subscribed, to become part of the community so that you can join the streams and just be part of all of the fun around the stream. I've been on vacation this past week, but I'll be resuming streaming again tomorrow, the day after this is posted, with the first day of our 1,000 subscriber celebration stream. I'm recording this in advance, but I'm absolutely certain that by this point I am very excited to get back to streaming, so I really look forward to seeing you all there. Thanks for watching, and enjoy the puzzle. So, people in chat are talking about the difficulty of Jovial puzzles and other assorted puzzles. So I think there's really sort of two things that are conflated by when people talk about difficulty, particularly in the context of LMD. And there could be really two separate ratings, one of which is familiarity, and one of which is the difficulty of the logic involved. What you actually see when you see the ratings on LMD is sort of the sum of how unfamiliar the puzzle felt versus plus how difficult the logic involved was. So a puzzle could use totally alien, unfamiliar logic that's all very easy, and it will still show up as 5 stars on LMD, or 4 stars sometimes if you're really, really, really nice. Whereas if a puzzle uses familiar mechanics and familiar logic, even if that logic is very difficult, it will often show up a little bit lower. And so when I see a puzzle that uses only familiar mechanics, then suddenly, and it's rated 5 stars, that is a little bit scarier than if I saw a puzzle that was like some Schrodinger cell chaos construction equal region sum line, who's a what's it kind of puzzle. And I think so. I think there's a very interesting distinction between setting like very good familiar feeling puzzles and very good sort of very alien feeling puzzles. But I think the difficulty, particularly on LMD, ends up looking very weird. Okay, so what are the rules of this puzzle? So we have standard Sudoku rules. Black dots mean the digits are in a ratio of 1 to 2. And so you could, for example, have a 6 and a 3, 8 and a 4, various combinations like that. White dots mean the digits are consecutive, so you could have a 6 and a 7, for example. Not all dots are given necessarily, so it could be, for example, that this is a 6 and this is a 7 and there's no dot. This is, if you're wondering why people always say this, by the way, when these dots started, they were often called kropki, which is, as I understand it, just Polish for dots. And those puzzles all included all dots. So there was a negative so there was negative information. So even though there's no symbol here on one of those puzzles, the fact that there's no symbol would actually encode information about the relationship between these two digits. But that's not the case now. I'd say probably now 90% or more of the puzzles you see that involve these dots will not have that sort of negative constraint. But because especially if you use the word kropki in your description, people will yell at you if you don't include a specific statement about the negativity or the lack of negativity. That's why we get the sort of none rule. There's a lot of sort of a lot of the writing the rules is in so that people will understand them is about knowing what rules to state aren't there. Because someone might assume that X, Y, or Z. I have to make sure I state, okay, well, it's not the case that that's a rule because I didn't say it. So anyway, so if you're curious about where that's coming from, that's where that's coming from. And last up, we have these diagonals. The diagonals are just extra regions, meaning that this diagonal is a full set of the digits 1 to 9. So digits can't repeat on this diagonal, digits can't repeat on this other diagonal. And that is it for this rule set. Okay. So we also have a 5, which is going to be a 5. So this is a very unjovy number of given digits to be given. But that is that. So I'm noticing these black dots all over the place. So whatever it is we're supposed to think about has to involve thinking about these cells. And so I know, among other things, that I have to fit 5, 7, and 9 in this pentomino in here because 5, 7, and 9 are not allowed to go on black dots. So, for example, because of the given 5, I know the 5 is actually pushed up into one of these cells in box 1. And 2 of those cells are on the diagonal. Hey, Grikez, are you at all related to the other GRKE setter? So yeah, so I think so you have to look at that. And so I think the point is it's going to be really hard in the process of putting 5, 7, and 9 on the diagonal in all of these places to not repeat 5, 7, and 9 on the diagonal. Right. So this box only has 2 non-diagonal cells that could have 5, 7, or 9. This box only has 2 non-diagonal cells that could have 5, 7, or 9. And this one only has 2 non-diagonal cells that could have 5, 7, or 9. And so I think the moral of the story is if these did not all contain 5, 7, or 9, then we're immediately broken because then we've put 4 5, 7, 9s onto the diagonal. So I think I got very lucky and I think I correctly identified the right question. So I can only put 1, 5, 7, 9 on the diagonal in each of these boxes. And the same actually goes over here. These have to all contain 5, 7, 9 as well, because again, if I put more than 1, 5, 7, 9 onto this diagonal, that's too many. Yeah, that's a very cool start. Now, we've already broken the puzzle. So that's not great. Because we now have a 5, 7, 9 quadruple in row 2. So clearly I have misunderstood something. What did I do wrong in my reasoning? Oh no. Let's see. Okay. Okay, so Naverio took 50 minutes, so we're going to be doing well if we can do 500 minutes. Okay, so we're going to erase that, and we're going to argue this again very carefully. I'm going to take away these corner marks because I think they're distracting for now. I can put 2... Oh, it's the box 5. Okay, box 5 likewise is pointing south. Okay. In box 5, actually... okay. It only works for this diagonal. Okay, so the diagonals are different as regards box 5. So let's look at this diagonal first, which is often called the positive diagonal, although that pains me because it has negative slope, but whatever. We're going to call this the positive diagonal anyway. So if I look at this diagonal now, then on this diagonal, actually, it is true. I have to put at least 1579 on here, at least 1579 on the diagonal here, and at least 1579 on the diagonal here. That means I need to put the other two off the diagonal in these cells. Okay, that part I'm happy with. But now this diagonal is different because this diagonal does not play nicely with the pentomino in the central box. So if I look at this pentomino, actually, there are actually multiple points where I could put something here. Okay. So Changeable says the slope of this this line is positive, and I want to explain why that's not true. What's the equation of this line? Or maybe here's a better question. What's the equation of this line? The equation of this line is I equals j, or if you prefer, y equals x. And if there's one thing I know about the line y equals x, it's that the line y equals x has positive slope. The change in x and the change in y move in the same direction. So this is the positive diagonal if you're naming things by the slope, because the way you count the way you count in a puzzle, this is row 1, column 1. And so this is the point 1, 1, this is the point 2, 2, this is the point 3, 3, and so on. If you want to call this the positive, that's fine, but then this has to be row 1 and this has to be row 1, column 1, which is not what anyone does. So if you actually think about slope, instead of slope as being just a like abstract idea, if you think about it as it's connecting the values of inputs and outputs or something like that, then yeah, this is definitely the positive diagonal, even though everyone says it the opposite direction. And it's because, again, the way we index this is upside down of the way we normally would. Anyway, we've got a bunch of pencil marks now. So now I think what we want to actually do is look at the fact that I can only put 1579 in these cells. So I have to put, in fact, I have to put a 579. In fact, actually, here's an even easier way. Where do these two cells go in box 1? They go there and there. Right, those are the only two cells that can have those two. So these are 579. That one's not 5. So I've already got two 579s on this diagonal. And now where's the last one? The last one has to go down here somewhere because I can only now put one more 579 on this diagonal. So I need to put two of them off like that. But one is on, which means this cell's definitely not a 579. So this is all the things that aren't 579. This is a Kropke number. Okay, so I want to make a color for definitely 579 and a color for definitely not 579, because I just want to color this blue rather than pencil marking it in that way. Because I think this puzzle is going to confuse me too much for me to simultaneously solve it and be a smartass, as much as that is my MO. But blue just means is not 579. And so I know this cell's not 579 because I know that on this diagonal, I've got one there, one down there. And that means this cell's not 579 either. So one of these two is 5, 7, or 9. Okay, and that means none of these cells are 5, 7, 9 because I've got my 5, 7, 9s for this row. Right, because I need to put 1, 5, 7, or 9 over here. So none of these are 5, 7, 9s. And also this can't be a 5, 7, 9 because of, again, one of these two is a 5, 7, 9. I don't know which one. I'm going to make things that are definitely 5, 7, or 9 yellow just recreationally. Uh, you're welcome to find that this is useful or not useful. Now, a cell across from a Kropke dot from a 579 is even, and so it is definitely not a 579, a white Kropke dot. So these are not 579. So that means this cell is 579. Uh, so that's cool. Let's see. That one is not. Uh, okay, where else do I have places where I know that there are or are not 579s? Let's see. I know there's two down here, one up here. Yeah, one of these two, one of these two, one of these three. Uh, oh, bet sell. We've got to do a bet sell. Let's bet on. Uh, sorry, I was messing with browser settings. We're gonna do this cell as our bet cell. We'll see if it's a good choice or not. Uh, may or may not be a good choice. Okay, what about column 7? Uh, could I possibly avoid having a 579 on this dot? Unfortunately, I think I could. Oh, hey, Jovial, how are you? I think I have valid pencil marks on your puzzle less than 15 minutes in, so I think I'm happy with how this is going so far. It's a very cool idea. Uh, it helped that I had a puzzle with the same idea, so I at least had a good place to start. Uh, oh Lord, sorry to hear that. Yeah, two of these are yellow, but that doesn't help. Okay, so X-wing of 5s in rows 1 and 2. Okay, yeah, that's a good point, Russ. I know the 5 is up here somewhere, and it lines up with this 5. So I actually do know if I want to hunt down this 5, I actually do know that there's actually a 5 in one of these. It probably is a good idea to try and hunt the 5s. Uh, oh, of course I was going to try this one. Did you see this grid? It was gorgeous. I'm sorry that I've ruined it by coloring all over it, but I have. Uh, let's see. So maybe I should think about what these digits are that are next to 5, 7, or 9. So is there any digit this absolutely cannot be? Well, I mean, to be clear, I know it's even. It's 4, 6, or 8. Uh, but none of 4, 6, or 8 break the ability of us to put two Kropke in here, right? Uh, yeah, if this were a 6, that would just make this. If this were a 6, that would make this 1, 2, 4, 8. Then this would be a 3. Am I supposed to be thinking about the leftovers here? No, because there could be two odds on these, but there don't have to be two odds on these. Uh, yeah, blue means it cannot be a 5, 7, or 9. Uh, so if you like, you can think of that is a black dot digit type situation. Uh, okay, so yeah, this diagonal I don't quite know. I'm trying to see. Okay, I know these two digits show up on this diagonal. Uh, so those two digits I know are these two digits. Uh, and oh boy, is this going to get tricky. If I have to try and pencil mark what pairs of yellow cells I know are the same, this is going to get tricky. Because that's the same pair as this. Oops, sorry. Let me do that carefully. Okay, these are the same. pair of digits, and that pair of digits is actually also this pair of digits. Now, let's see. Can I put that pair of digits anywhere else? I don't think I know it's this pair of digits, as tempting as that would be. This is the third digit. That's not one of those. Right. This is the other one. We'll make that the purple one. And so, as Dictionary points out beautifully, this cell now sees all of the 579s. It sees the two orange ones, and apologies for this coloring in advance, but it sees the two orange flavors and it sees the purple flavor. So this, we actually know, sees every kind of 5, 7, and 9. So it's not 5, 7, and 9, which means this is 5, 7, and 9, and it's the purple 5, 7, 9. Which means that this is an orange 579. And so, yeah, let's see. So this is an orange and a purple one. There is a purple in one of these two cells. Let's see, 5, 7, 9, triple in row 7. Ah, beautiful, beautiful. Okay, Barbie spots that we've now put 5, 7, and 9 in this row, which somehow I should have appreciated, but didn't. And purple is now forced in box 7. Because purple is already on the diagonal, right? That's the point about purple. Purple's already on this diagonal. So purple can only go here. So the other one of these is orange. Whichever it is. Okay. So can this be 3 yellow cells? Otherwise, this has... Oh, I guess there are either 3 yellow cells here or 3 yellow cells here. There are 2 oranges because I was unable to identify... I couldn't disentangle this set of cells, but I knew this pair of cells was the same as this pair of cells. I agree in a perfect world I would have 3 colors, but if I wanted to have 3 colors, I would have to do something like say, this is the green one, this is the blue one, and then say this is a green-blue pair, which would look like that, and that seems messy. I'll do it if I have to, but I don't yet have the way to connect it. I suspect I'm going to, once I figure this out, be able to connect things around the grid, and then I can probably go into 3 colors. Let's see. Purple is one of the 579s in row 5, so the bet cell is not 579. Right. The purple is one of these two. Okay. So Derek has a good point. Purple in box 5 can't go on this diagonal, so it has to be one of those two, which means this cell's neither purple nor either orange. So this cell is blue. So that is cool. Let's see. We're close on having like all the 579s placed in the grid, which would be really cool, of course. We know 2 of them are here. I know one of these 2 is purple. Let's see. I know purple is in one of these 3 cells. It's not immediately helpful. One of these 2 is yellow. Let's see. Is there any way I can chase this given 5 around more? I would really like to be able to chase this given 5 around more. Like, it would be really great, for example, to be able to know whether purple is 5 or not. Well, I know 5 is in one of these 2 cells down here. So I know 5 is in one of these 3 cells, at least. One of these 2 is yellow of some flavor. But I don't know which one. So it's going to ask if 5 is purple. Where does it go on this diagonal? But if 5 is purple, it goes there on this diagonal. Yes, yes. Debating if I'm supposed to know something about this. I don't think I do yet. So maybe I'm supposed to now ask about the flavors of these dominoes and whether they can be, in particular, 3-6. Because 3-6 is interesting, because 3 and 6 only go together on blue dots. Or sorry, on dots. Let's see. Nicholas asks if row 5, column 7 can be yellow. I don't see why it can't be, but I would love to know that it can't be. Uh, uh, why can't this be yellow? It's looking at these two include a purple, so it could very well only be looking at 2 of the 3 flavors of yellow, as far as I can tell. Hey, Ablichka. Welcome, welcome. We're off to we're doing a just beautiful Kropke puzzle here. Let's see. Memerister is suggesting looking at black dots in these Z's. Uh, uh, let's see. The 5 blue in row 8. Yes, Rick. By the way, welcome, Rick. But blue doesn't, sadly, in this puzzle mean even. Blue in this puzzle means not 5, 7, or 9. So I need one more blue to know that I have exhausted my supply of blue. Although that is a good thing to look at, is looking for places where once I get 6 blue, then I know that I am done with blues. The 2 yellow oranges in column 8. So yeah, purple is in one of these 2 cells. But I don't see what's wrong with this being an orange 579, Nicholas. So yeah, I'm trying to figure out where did the is there anywhere where the Kropke dots are sort of pushing each other around? But I do not think so, unfortunately. Nothing that I can see anyway. Now I probably can prove one of these has to be 3-6, right? Is it possible that none of these are 3-6? It is not possible that none of these are 3-6. Because if none of these were 3-6, then 3 and 6 would be here in box 1. And then one of them would have to be here in box uh 3, and that's not going to work. So one of these at least is 3-6. It could be that 2 of them are 3-6, as far as I can tell. Let's see. Nicholas says row 4, column 7 has to be blue. the other yellow is in row 5 or 6. I don't see how you know that, Nicholas. Let's see. Okay, so now Russ is looking at this a slightly different way, which is to say that in opposite sides, these can't be exactly the same 4 digits. And I guess this is a different way of saying the same thing I was getting at, which is these can't be the same exact 4 digits, because if these are all exactly the same 4 digits, then those 4 digits all go here, which is not great. Uh, oh, let's see. Did I misconstrue what Russ was saying? Oh, Russ was making the point, but on the diagonal. Thank you. Afraid not. If these were the same set of 4 digits, those 4 digits would get placed in these 3 cells, which would not work. So that's interesting. These 4 cells are not the same as these 4 cells, and they're also not the same as these 4 cells. Could they be the same as these 4 cells? Unfortunately, I feel like this domino could be equal to that domino, and this domino could be equal to that domino. And that doesn't immediately look problematic to me. Yeah, I think, Nicholas, I think this can absolutely be yellow. I don't think there's any problem with it being yellow. We don't have any idea what color 5 is yet, which is really the source of a lot of our woes. Uh, yeah, let's see. Okay, so here's an interesting point. This domino, I'm going to make it green just for sake of exposition. Where does this domino go in box 3? Well, this domino in box 3, it can only go in these cells. So at least one of this domino is on this Kropke dot. So there is a common digit between these two, possibly 2 common digits. So actually, this domino is special because it looks at 3 of the cells over there, which is not something that happens often. Is it something that never happens again? That might be the only place that happens. Am I blind? I don't see another place. Oh, it's probably because I haven't finished the coloring yet. But yeah, this domino. Yeah, this domino looking over there tells us it's got to go in one of those places. See, I guess I also can ask, where does this domino go on the diagonal? Is that a reasonable question to ask? In fact, maybe actually, sorry. Maybe the correct question to ask is let's change our tech. Uh, these 4 blue digits, where do they go on this diagonal? Well, they go in 4 of these 5 cells. So at least one, I guess that's not super exciting. I don't think that's quite the right way to look at it. Can both box 1 and box 9 have a 3-6 dot? No, it is not possible. So Carl observes, continuing to observe. Box 1 and box 9 cannot both have a 3-6 crop key. Because if they both had a 3-6 crop key, I would not be able to put 3 and 6 on the diagonal here. If neither of them has a 3-6 crop key, then we break box 5. Because now once neither of them does, then we'd run into the problem that these would be a 1, 2, 4, 8 quadruple, and I'd have to put 1, 2, 4, 8 on here. Okay. So I know that 3 and 6 show up exactly once amongst these 8 cells, which means that no, sadly, it does not mean it doesn't immediately seem to mean anything to me that I can tell. So no dot in box 5 has a 3-6. I'm trying to see if I get there. So one of these is a 3-6. But I could put, say, a 3-6 here and here, right? That's fine. I don't see why that's not okay. Uh, Now, almost assuredly, we should think about the same thing with box 3 and box 9, and maybe that'll get us further. So in box 3 and box 9, we also can't have no 3-6s. And we also can't have... Oh, actually, I think this is different. Because one of these is yellow. We actually... Okay, so I think this might be the point. What combination... So there's only 2 blue cells here to go in box 5 on this diagonal. I don't know which it is that's yellow yet. Sorry, I can't quite get it. I'm going to read Calzone's point. If neither of the black dots in box 9 is 3-6, then we have both 3 and 6 on the diagonal in box 9. So where do you put 3 and 6 in box 5? Okay, so let's look at this. So Calzone is saying it's broken if I don't put 3 and 6 here. So I would put 3, 6 here. I'd go 6 there, 3 there. Now that would mean that in box 5, yes, this is very closely related to what we were looking at before, because now where do 6 and 3 go? In box 5, they go here and here, but that's broken because then I don't have a place for my third 5, 7, 9. Gorgeous. Okay. So one of these, that is an excellent spot, Calzone, and an excellent way to do this. One of these dominoes is a 3-6, so this is not a 6. And welcome, Ethan, to your first zetamath stream. I hope you enjoy it. And you are Toast Crush. Okay, I know you from the Discord. Okay, so this is 4 or 8. Now, this being 4 or 8 tells us, of course, neither of these is a 4-8 sort of Kropke dot. So one of these is 3-6, and the other one has to have a 2 on it. Because if you can't be 4-8, then there has to be a 2 over here. Okay. So this cell is then going to be uh ah well, I need to put an 8 in one of these two cells. Because if I can't put 4 8 on a Kropke dot. I can't put 8 on a Kropke dot. So the 8 now is pushed off the diagonal in, well, both of these boxes. Uh, and this can't be an 8, because if row 9, column 9 is an 8, it makes this a 4. Oh, wait, no, sorry, that's fine. If this is an 8, that's a 4, and one of these is a 1, 2. That seems okay. Uh, okay, is there any chance? No, we're not going to be able to reproduce Calzone's argument about the 3 6s over here, or anywhere else, are we? Actually, maybe not. What if none of these are 3 6? If none of these are 3 6, then I put 3 and 6 on this diagonal. So then 3 and 6 are both pushed off the diagonal, and that doesn't work. So yeah, actually, Calzone's argument works very well over here too. There has to be a 3 6 on one of these Kropke dots, because if there's not, it breaks box 5 for almost exactly the same reason that it broke box 5 before. Oh wait, no, that's not true. Never mind. Sorry. It does not work. The argument doesn't work, because I could put 3 and 6 on the same one, and that would not be a problem because of the geometry. Never mind. Uh, okay, so the 3 and the 6 have to go on this diagonal somewhere. They're not going in this box. So, uh, so, okay, so I agree with Nicholas's point. Sorry, not Nicholas, Barbie's point. Okay, where are the 3 6 going on this diagonal? Well, I can put at most one of them across all of these cells. If I put one in one of the Kropke dots, I have to put the other in one of the Kropke dots, and so it's done. If I put one in the center, I can't put one on either of the Kropke dots. So there's always a 3 6 up here, which means there's no 3 6, of course, in either of these places. That is a great spot by Barbie. So neither of these is a 3 6. So one of these now is a 3 6 by our argument from before. Because if neither of these were 3 6, then this would be a 1 2 4 8 quadruple in both boxes, which would make this a 1 2 4 8 quadruple, which would break because that's too many cells. So as soon as these aren't 3 6, or sorry, as soon as one of these is a 3 6, this is a 4 or 8. And as soon as this is an 8, we get an 8 on this diagonal as well, in one of those two cells, which now says that there is an 8 on one of these dominoes. So one of these is an 8 and a 4. And in fact, the same is true in this box, because now actually this box has 8 ruled out of all of these cells. So 8 is in one of these cells. 4 is in one of these cells. And once 4 is in one of these cells, this isn't a 4. And we have a digit. That cell has to be an 8. I'm going to dance and wait for chat to tell me that that's wrong. But I think it's right. I think we chased the 8s around. Watcha! I've made it 15 seconds and no one has told me it's wrong yet. So excellent. So that's an 8. So that's not an 8. Which means this is an 8. So ergo, this is not a 5. This is not a 5. Okay, yeah, one of these is a 4. This is an 8. Uh, okay, so now what's the other one? So the other one here. Okay. So now let's think about box 9. And so this is Calzone is pointing this out. In this box, we have a 3, 6. What else do we have? Well, we don't have an 8. So we either have a 1, 2 or a 2, 4. Which means that this cell is either a 1 or a 4. Except we know the 4 is on this diagonal, so it's not a 4. It is a 1. And so, in fact, actually, we can spell out that this is a 2, 4. Oops, sorry. This is a 2, 4 and a 3, 6. In whatever order, I don't know yet. So that's cool. This 8 looks over and, of course, says that these aren't 8. So that means these aren't 4. So actually, the 4 is in this row in this box. So these aren't 4. So these aren't 2. Uh, let's see. 1, 2 pair in box 1 because of the 8. Let's see. The 8 is not placed there or there. I don't quite see that yet. 1, 2, and 4, 8 on the dots. Yeah, I do know that. Okay. Once there's not a 3, 6, I know that one of these is 1, 2, and one of them is 4, 8. Okay. And so got it. Okay. This is someone elaborating on Barbie's point. Once this is not an 8, this has to be a 1, 2 pair. So this is a 4, 8 pair. Good. Now, once this is a 4, 8 pair, this can't be a 4, 8 pair anymore. So this is my 8 and my 4. Uh, So now where is 4 on this diagonal, asks Jay. 4 on this diagonal now can only go here. So that goes ahead and gives us a digit. So now 4 in this box is in this row somewhere. And now this has to be 3, 6 because 1, 2, and 8 are all gone. So this can't be a 4, 4 Kropke dot. This has to be a 3, 6 Kropke dot, which means that's not a 3, 6 Kropke dot. In fact, it has to be a 1, 2 Kropke dot because there's just nothing else left for it to be. So these digits up here are a 5, 7, 9, and a 3 and a 6. So I can go ahead and mark that the 3 and the 6 are up there. So there's a 3, 6 down here. No, there's not a 3, 6 down there. Never mind. Don't listen to me. I can't do Sudoku. Barbie has the clutch point next, which is that this can't be 3, 6 anymore because it looks at a 3, 6. So this is not 3, 6. So that means it is 4, 2, which means that this isn't 2 and that's not 4. So this is 3, 6. Excellent catch. Okay, so 2 on this diagonal has to go in one of these places. I don't feel great about that deduction, but we'll make do. White dot in column 7. Ah, that's probably a good question. What is this? So it can't be 1, 2. Can't be 2, 3, 3, 4. Could be 4, 5. Sorry, could be 4, 5 or 5, 6. No, can't be 5, 6. Sorry, could be 4, 5. Can't be 5, 6. Can't be 6, 7. Can't be 7, 8. Can't be 8, 9. So this just is 4, 5 by magic. Okay. That's just the only possibility. I love it when that happens. And so now purple is not 5. So now definitively 5 is orange. And actually we can place the 5 there and there in those boxes using that fact that 5 is when we know 5's down here. So we know that 5, yeah, that's a 5. So we get lots of orange 5s. Okay, so these two digits are in fact actually the same. Okay, so we're going to go ahead and upgrade these with a green flash to indicate that they're the same. Actually, I guess I don't need that. All I really need to do is just unorange 5s. I don't know. Whatever. These are the orange 7, 9. The orange 7, 9 is a digit. So the orange 7, 9 goes up here somewhere. I could just talk about the orange 7, 9. I don't need to be too fancy. So this is a 5 because it sees the orange 7, 9. There we go. Okay, so this is not a 5. Okay, so now now I know purple is in here, right? Yeah, purple is in one of these two cells. So this digit sees purple and both oranges, so it is blue. Because one of these two is purple. I don't know which one. But that means this digit sees all the 5, 7, 9s. Of course, that's not a 5 anymore. Yes. Now where does 5 go on this diagonal? 5 on this diagonal now can only go here. Because, well, I don't know what to say for you beyond that. It can only go here. It's ruled off of all of the other places. So these are the 7, 9 flavors of that. So that's a 4. That's a 5. So that is my last yellow for this row. So these are all blue. And that's blue because oranges are blue. Or sorry, because it's blue. This is the last blue for the column as well. Sorry, last yellow for the column. So that is that. In fact, this I know is a 1 or a 2 just by the column considerations. So this is blue. Right. And this 4 now places 4 and 8 in box 5, as many people in chat are pointing out. Because I knew 4, 8 was on one of these dots, and it's no longer this one. Let's see. 4 is now over in one of these two cells for whatever that's worth. Let's see. So this is either an 8 or a 3 or a 6. Just in terms of blue digits that this cell could be. Hey, SBQ, welcome. We are doing a very cool Kropke puzzle. Let's see, 5 goes in one of these two cells. This isn't a 5 anymore, so 5 goes in one of these two cells. Don't know which of these is orange and which of them is purple yet, although I suspect I probably will soon. Let's see, what can this be? Can't be 1, 2. It could be 2, 3. It can't be 3, 4, or 4, 5, or 5, 6. It could maybe be 6, 7. But can't be 7, 8, or 8, 9. So this is either 2, 3, or 6, 7. Those are the only options. Do I know which one it is somehow? I don't think I do yet. The 4 on the diagonal eliminates the other possible 4 in box 1. I don't see what you mean. Neither of these is on the diagonal. Row 3, column 4 is a naked purple. Okay, that is the claim. Okay, so... well, it's not a 4, so this is a 4-5 pair. And so, yeah, so this is a naked purple. Great. Okay. That was not as hard to see as I thought it was going to be. So this is the orange flavor. This is the purple flavor. Okay, so the rest of this column is blue. Let's see, so I got to put a lot. So the purple, yeah, the purple is placed here. That's the purple. So that's not the 5, because 5 is not purple. So that is the 5. So I need an orange 7, 9 to go in one of these two cells. I need an orange 7, 9 for row 8. It's got to go there, which makes that blue. So now the orange 7, 9 is in one of these two cells. Let's see. You might be just a smidge behind, Nicholas. And welcome back, Andrew. So I need a purple in one of these two cells. These are blue, I know, because I've got all the yellows for this column. Let's see. Okay, so yeah, this diagonal is getting quite full. The things that are left on it are just 1, 2, 3, 6. Let's see. Can I rule any of those out? Well, I know this is not a 2. Because I know I need a 2 on this diagonal somewhere. This is not a 1, because there already is a 1 on this diagonal. Let's see, for that matter, let's fill in candidates here as well. This is not a 1. It could be a 2. It can't be a 4. It could be a 3 or a 6. So this is only a 2, 3, 6, apparently. Let's see, if this were a 2, that would be a 1. Otherwise, this will be a 3, 6. 4, 5 pair in box 2. Ah, yes. Okay, beautiful. So yeah, so the 5 here comes up here, 4 or 5. So that's the blue one. That's the yellow one. It's orange. Yeah, I have barely thought about this center cell, I admit. So it has never seemed appealing. That places a 4 down here, so that's blue, which makes this the yellow-orange 7, 9, which makes that blue, which makes this the 7, 9. So that's not a 3 or a 6. So these are, in fact, a 3, 6 pair. Uh, so these are a 1, 2, 8 triple, for whatever that's worth. That one's not an 8. Where does 8 go in column 6? 8 in column 6 now only goes here. So that's an 8. So that's not an 8. So now the 8 is placed down there. Oh, interesting. So I'm way off the intended solve path? Because this has felt so smooth. I was sure this had to be exactly the intended path. Apparently we've gone way off. That is the conclusion. So yeah, this is 2, 3, or 6. This is not a 1, I can confirm, because there's a 1 in the row. This were a 3, 6, that would be a 2. So a 2, 1, that would be a 3, 6. That seems fine all around. Let's see. 8 in box 8. We got the 8 in box 8 after some adventures with the 8 in box 8. We did find it. Yeah, one of these two is purple. I don't know which one. One of these gajillion is purple. I don't know which one. Uh, well, I've greatly enjoyed it, even if I've been on the wrong path the whole time. I thought it all seemed to follow from very natural questions to ask. Okay, let's look at our diagonals again. Do I know anything new about the diagonals? Let's see. I know one of these two is a 1, so I might... It's possible I'm supposed to be using diagonal tricks. Like, I know this cell... okay. In fact, beautiful. One of these two cells is a 1, because there has to be a 1 on this diagonal, and everywhere else is ruled out. So that says this cell that I'm hovering over isn't a 1. But now 1 can only go one place in column 6, and it's there. Oops. And it's there. There we go. So this cell now is a 1. So that makes this a 3, 6 pair, which makes that a 2. So that's a 1, that's a 2. So now this digit is a 3 or a 6 to finish the column. Let's see. Okay, so now I have the 1 and the 2. So this is not a 1 or a 2. It's a 3 or a 6, which means this dot can't be a 3, 6 anymore. So it's a 1, 2. This is not a 2. Okay, we've got our 3, 6 there. Okay, so now I'm noticing, well, never mind. There's a 3, 6 pair just looking at this. So that's not super exciting. Column 1 now has a virtual 3, 6 pair. Uh, yeah, this is a sweet puzzle. This is a favorite. This digit's just given. I should probably write that in rather than thinking about other things. This is a 2. So this is a 1 by the row. So this is a 3 or a 6. I might need to color the 3 6s. Coloring the 3 6s is definitely on the list of things I am willing to contemplate doing. I just wanted to just check real quick and see if anything else was going to pop up before I started coloring 3 6s. Okay, these are a purple 7 9 and the other 3 6. Okay, got it. So here was a point that was made by someone in chat that was beautiful, but I didn't see how to use at the time. Which is that there's a 3 6 here, and I know that this is either a 2 3 or a 6 7. So the other 3 6 in the column is here. And so apologies to whoever in chat it was that said this, that I didn't see how to do it at the time. That cell has to be a 3 6. And so now that gives us that this is the purple 7 9, which now places the purple 7 9 here, which places the purple 7 9 here. Which blues this cell. Which every time I say, I think of the line from Arrested Development, where he says, "I blew myself for you, Michael," which is just ever on my mind, as it is such a beautiful line. The other 3 6 in column 8, where does it go? Well, the other 3 6 in column 8 can't be there because there's a 3 6 looking at it, so it's there. So that is cool. Okay, I have a 3 6 pair in column 3, so this is a 4 or an 8. Let's see. Okay, this cell is not 3 or 6. Let's see, this is 1 or 2, not 3 or 6, not 4, not 8. This just is 1 or 2. That's it. Row 5, column 1 is restricted. It's not a 2 anymore. It's not a 7 anymore. Got it. Okay. Because of the 7 9 pair. A 7 9 pair is looking at this digit. So this digit is in fact a 3 or a 6, which gives us a 3 6 pair in the row, which gives us that that's an 8 and that's a 4. Beautiful. That's a 1 to finish the row. That's a 2. Oops. It's a 2. That's a 1. Now, to go with a 3 or 6, this can only be a 2 or a 7. Let's see. Okay. And now this is a 2. Thank you, Logan. It's a 1. That's a 2. It's a 1. I know Logan is always worried about typing quickly enough, but you definitely typed the coordinates of that cell quickly enough. The dog wanted to chase the shuttle bus. Is the shuttle bus going somewhere the dog wants to go? Let's see. This cell has to be a 2 or an 8, and it's not a 2. So this cell's an 8. So that's a 4. That's an 8. This cell here is now a 3 or 6, so it's the other 3 6 for this box. This 2, got it. Okay, this 2 now is going to finish everything. So this 2 is going to tell us that this is not a 2, it's yellow. And so this is the orange yellow. And so that's blue. And so that's the orange, yellow 7-9. And so that's blue. And we finished our coloring, at least. So this is 3 or 6. This row needs a 2, so that's a 2. So let's see. So, yeah, this is a 7-9. Thank you. Let's see. Okay. So now we are in pretty good shape, I want to say. Now, the whole point of the entire puzzle is this cell. Because this cell, which is just the orange 7-9 that we've been hunting the entire time we've been solving the puzzle, is consecutive with a 3 or a 6. And ergo, all orange 7-9s are 7s. I knew that, everyone in chat who was pointing this out. I just wanted to finish my coloring and then fill it in all at once everything has been done. You don't fill in digits until you're done your coloring. It's like eating your vegetables before your dessert. It is just an important thing for us to do. So that is a 9. And now, I suppose I could have colored 3 6s, but we're not going to need to anymore. I don't think, because now we can go ahead and just breeze through the 3s and 6s, using the fact that 7 is only adjacent to 6. 6 3, 6 3, 6 3 6, and then we're done. Wow. Wow, that is spectacular as a puzzle. I'm trying to think of words to say about this puzzle other than how much I enjoyed doing this. But yeah, that was amazing. I'm happy that I set a puzzle where the entire point was that you can't put 5 7 9s on black dots, so that I spotted the break-in, because I don't think I would have spotted the break-in if I hadn't set a puzzle where the break-in was similar. This puzzle's better than mine, though. But if you're curious, my puzzle is 5 7 9. It's on LMD, I'm pretty sure, under the name 5 7 9, which is also about 5 7 9s and black dots. But yeah, the way everything hangs together here is just great. I'm really curious how off I was on my path versus Jovi's path, because everything I did felt completely normal and natural. Yeah, that was amazing. Yeah, this is a great puzzle. I would have thought 2 to 10th. I would have thought I remembered you doing my 5 7 9 puzzle where you had to color for could be on a black dot versus couldn't be on a black dot. But anyway, spectacular. I loved every minute of this one. It felt really nice. I don't see how this was a 5, though. Like, this is way easier than most jovial puzzles, I feel like, at least for me. Like, it didn't feel like... Like, where was the 5 part? LMD rating, difficulty ratings always sort of befuddle me. All right. Well, next up we have